And now I ask how many gaps there are which are greater than 1. See, there I looked at partitions where the gap was at least 3. And then I asked how many gaps are strictly greater than 3. Now, distinct part means the gap between the parts is greater than or equal to 1. And now I'm asking how many parts are strictly bigger than 1. If there are k parts, I count this partition with weight. Same formula. 1 plus b to the power of k, b to the number of parts. Okay, so there is a certain parallel development here. And when I sum this over partitions into distinct parts, I end up with this. That, to me, is the partition theorem, which is Lebesgue's identity. And this was stated for the first time. So if I now put b equal to 1, my weights are powers of 2. So my conjecture would be I have now a two-adic representation for this generating function. The partitions where the evens don't repeat. So I went up to Basil Gordon and I said, as per your theorem and as per my philosophy, the number of partitions of an integer n in which the evens don't repeat is almost always even. It's odd precisely at the triangulars. It should be almost always a multiple of 4, almost always a multiple of 8, and so on and so forth. And the answer is yes, by the same method of modular forms, and you can use this technique. So I just wanted to give you this parallel, but my observations were strictly combinatorial. I didn't use modular forms and I didn't use any Q-theoretic techniques. Okay, so I just wanted to stress that. All right. Let me do one more before I come to this new companion. There is another way in which you can generalize the Euler pentagonal numbers theorem, and that is this Jacoby triple product identity. Probably one doesn't see the pentagonal numbers theorem immediately here, but if one dilates and one rewrites this identity in this form, then you will see that this is indeed the pentagonal numbers theorem. Because when I put z equal to -1, these three products combine to give you a single product. So Jacoby's product identity for theta functions may be viewed as a refinement of Euler's pentagonal numbers theorem. And now, there is the special case of the first identity, which is this. And here I have used Euler's theorem, and I have rewritten it in this form, right? That is equal to this product by Euler's theorem. So this series, q infinity divided by minus q infinity, yields the perfect squares. And that's going to be the dominant theme for today's lecture. I again bring you back to Ramanujan. It is said that Ramanujan knew, if not the circle method, he knew that the number of partitions of n could be evaluated exactly. The reason R. Hardy felt that way was, in one of Ramanujan's letters to Hardy of 1913, he actually claims that if you look at the reciprocal of this product, we are then counting partitions, ordinary partitions with weight, in my view, 2 to the number of parts. Okay, number of different parts. Ramanujan claims he has an exact formula for this. So this has a very important history. This is there in Ramanujan's letter to Hardy, the reciprocal of this, and that is the genesis of the circle method of Hardy and Ramanujan, this particular identity. Okay. All right, so that is just put there, not just for historical reasons, but we are actually going to use it in the proof. All right, so now I'm going to give you a very nice 2 new companions to Euler's pentagonal numbers theorem, and these are both quite deep. I was visiting Bruce Bent at the University of Illinois in Urbana, and as you know, Bruce Bent lives within Ramanujan's notebooks, and now he's living within Ramanujan's lost notebook, having completely digested the original notebooks. So he showed me this identity, and one of the students was working on this, and the question they asked me was, Krishna, what is the partition interpretation of this identity? Can you say something about what this means in a partition theoretic form? So I looked at it. The first thing I wanted to do was study a special case. So I said, let's put A equal to 1. If I put A equal to 1, this is the series that I get. And I'm just going to spend 1 minute giving you the combinatorial interpretation. q to the n plus 1 over 2. What is that? Well, that is the n plus 1 over 2 represents the minimal partition into n distinct parts. That's the way I like to look at it. The smallest partition into n distinct parts is 1 plus 2 plus 3 up to n. So I draw the Ferrer's graph, and now I can insert columns of length n, any number, columns of length n minus 1, any number, and so on, and I will generate all partitions into n distinct parts. So the generating function for all partitions into n distinct parts is this, divided by 1 minus q, 1 minus q squared, up to 1 minus q to the n. Now that is not what we have here. We have a slight variation.